Olaf is a senior consultant at Integrated Vehicle Safety with TNO in Eindhoven and the Netherlands, and will present an in-vehicle nudge to direct drivers' attention. Olaf, good to have you here and keen to hear what you found out in the project.
Thanks a lot to you all. Yeah, let me start to state that I'm extremely proud of all the partners in the MeBeSafe team that have been dedicated over the last years on making this work in a really challenging domain. I think we all learned a lot, and only that is already a huge accomplishment of this project. Furthermore, I'm very pleased to share with you the results of the nudge for driver attention today. One of the objectives of the MeBeSafe project has been to design, develop, implement, and evaluate an in-vehicle nudging system to improve the timely attention of drivers in vehicles to potential hazards on the road, especially in interaction with cyclists. And that, of course, very well fits the ambition of the MG 3.5 call text in 2015, the ambition to reduce the number of car-to-cyclist accidents on the roads in Europe by a large-scale implementation of such solution. I will spend about 25 minutes in introducing to you the nudging solution and share with you the results of a field operational test that we performed. And thereafter, Bram Bakker of Cygnify will get the floor to indicate the results of the cyclist prediction model and the test that we run with that, which can be seen as an option to our nudging model. If we go to the next slide, it appears that failure to look properly is a major causation factor in about 30% of the accidents on the road, especially in urban traffic at lower speeds. And the reason is that these lower speeds might give the drivers a false sense of low risk, while the risk in the urban area actually might be very high because of the fact that road users might appear from actually behind from any direction, from behind any view blocking obstruction like buildings, parked cars, or other objects on the road. And although actually it is a failure to look properly, that is never or seldomly an intentional violation of the rules. So what we would like to do is to provide a solution that continuously gives a low-level input to the driver to direct the attention in the correct direction. And we wanted to have that low-level input to prevent information overload to the driver, so that the driver can concentrate still on the main part of the driving task, and also to avoid alarm degradation. If you get a flashlight every few minutes, then you might not pay attention to it anymore in the further course of the drive. I really need to stress that such a system is in addition to already available advanced driver assisting systems, not instead of them. Go to the next slide. Because these current state-of-the-art advanced driver assistance systems already support the driver to avoid or mitigate imminent collisions. But these systems can only work properly when the safety margins already have become very small. So if the time to collision is, let's say, smaller or drops below about 2 seconds, then these systems might provide a harsh warning system to indicate to the driver that the driver needs to take control and attention. But if the driver does not take over and the time to collision drops even further down to 1 second, then there's a real harsh response by, for instance, braking in an attempt to avoid the collision. Now, if we make one additional click, And we see that in this project, we wanted to provide nudges in a way that the driver can better anticipate to the environment on the road, to all the different road users and potential hazards, and that safety margins stay larger, so that it's prevented that those small safety margins occur in which only harsh measures are possible. If we then click. To do that, we set up a system basically continuing out of two elements. First is the information provision to the driver through a human-machine interface. And what you see here as a kind of schematic is an augmented reality projection on the windscreen of a vehicle that shows a safe corridor of driving, where green indicates large safety margins and the yellow and red areas indicate decreasing safety margins. And this is a possible way of nudging drivers to drive and behave safely on the road and pay attention to those areas that need actually attention. So that's part of the HMI design in this project. But of course, the HMI needs to be provided with inputs to make sure that the HMI changes with the situation. And that's the lower part. So we set up a static hazard model by identifying potential hazards related to the road layout and the traffic rules. We set up a dynamic hazard model that actually merges the static hazard model with actually perceived cyclists in the field of view of the vehicle. And we developed a cyclist prediction model to predict the behavior of those cyclists that were observed over the next seconds, for the HMI to better anticipate on changes on the road. We then go to the next slide. We see the definition of hazard, because it's all on directing the attention of drivers to potential hazards. Well, a hazard is a source of that potentially causes injury, and predicting this hazard requires information regarding the road layout, the traffic rules. It might include historic traffic flow information related, for instance, to the time of day. Flow changes with how busy is on the road. So rush hour, you will have higher flows, which potentially leads to a higher level of hazard. And it also requires the trajectory projection of road users, in this case cyclists. Going to the next one. This is the system architecture that we set up and that we used. So we make an implementation in an actual vehicle, and for that connect to the CAN bus of that vehicle, and this CAN bus will contain the signals related to whatever the sensors of the vehicle see for traffic situation on the road. That can be radar, can be camera, and of course that is information needed as input to our system. We connected that to map information to get a better view on the infrastructure layout, and we use OpenStreetMap for that. And here you see different blocks that make an interpretation of that of all that type of information coming from the information layer as output to the decision and control logic of the HMI. Now in red, that's the branch more dedicated to actually predicting behavior, and the green blocks are more dedicated to the static and dynamic world model. If you go to the next slide, then this is the approach that we followed during the project. On the left-hand column, you see the actions that were actually needed for getting access to the sensors of the vehicle, to set up the different models, to design the HMI, and to implement the complete integrated system into a vehicle. But we also had, and that was very worthwhile in this project, an additional task as a parallel path, a selection framework where we used a simulator to get, let's say, to be able to select the best possible option for an HMI to be implemented, and we used simulations to calibrate the different models that we used. Go to the next one. So I will go now through each of these different tasks and show the results of these tasks before showing the results on the road. It was actually Office in this project that was responsible for designing the HMI. We started with a workshop with all the project partners to see and to brainstorm on different options. And 6 of those options were further worked out, and you see those options in this slide. Several of them intended to be included in the cockpit view of a vehicle, and others which we do expect to have, let's say, a better effect on drivers as a head-up display in a vehicle. So if we make one click, then these are the 3 actually that were worked out in more detail, and that were also used later to be checked in the driving simulator. Just remark on the upper right corner, that would be a head-up display with these green and red corridors. We had and have high expectations of the effectiveness of this HMI, but we also knew already from the beginning that it would be infeasible within the scope of this project to really make that implementation in the vehicle. So we kept that HMI option actually to benchmark other options to it. So on the next slide, you will see the HMI selection that was actually performed in a driving simulator study by CRF in cooperation with FCA. And that driver simulator study was used to evaluate the driver's visual behavior and judgment with and without a nudging HMI, and to determine the effect of the different previously presented HMI options in that simulator. There was an eye tracker included in this study to see what the gaze direction of the driver in all these different tests was, to get an indication if this HMI would be able, at least in this test setting, to direct the attention in the correct direction, or the direction that was indicated by the HMI. We used really common accident scenarios for cyclist to car interactions, and indeed it was shown by CRF that the augmented reality option in the lower part had a real good effect on directing driver attention. But good to know here, and also already as a result of this study, it proved that the other options also had a significant positive effect on being able to direct the direction of the driver attention. So that was more on the HMI selection. If we go further, we find some development on the static hazard model performed by TNO, where a hazard is a product of 3 different factors. And I would like to focus on the 3rd factor, the probability that a cyclist appears at a certain intersection based on flow data, for which we performed measurements in the inner city of Eindhoven for a very typical intersection. And you see in the center graph the flow data of cyclists making different maneuvers at that stage over a period of 1 week. And we used those flow data in that static hazard model, and you see the result of that static hazard model in the right graph as a purple line, escalating the hazard from, let's say, a distance of about 40 meters in front of the intersection, peaking at about 15 meters before the intersection. But of course, this hazard escalation very much depends on not only the potential hazards in the environment of the vehicle, but also depends on the velocity of the selected speed by the driver in that certain situation. Now, if we look to the next slide, it was a virtual vehicle that used this static hazard model to evaluate more than 20,000 conflict situations to see how the hazard model behaves in this type of situation. And there we concluded that because of the way of the driver behavior was modeled, that in this case the static model underestimates the hazard level, although in reality cars hardly brake in such situations where a higher hazard level is then indicated by the model. Very valuable information to be included and calibrate actually our static hazard model. In the next one, we see a result of the stochastic simulation study that was performed by BMW Group, looking more to the dynamic hazards simulations. Also here, many simulation runs were performed, and just one of these results showed that at a time to collision of 3 seconds, so reasonably close to a potential accident, natural variations in speed of vehicle and cyclist only lead to a collision risk of about 25%, which also indicates that this uncertainty makes it very difficult to predict the actual collision risk at an early stage, and also shows, and if you click one step further, it also shows that the ADAS, current ADAS systems are not able to address this fully, but that nudging in this case is a very valuable and valid option to be included. Going to the next one. Here you see the actual implementation in the vehicle with a very good collaboration between FCA, Cygnify, and TNO. You see a kind of head-up display with the selected HMI option that was mounted as a retrofit option here between the steering wheel and the windscreen. So in the end, we were able to make it in the type of head-up display to make sure that the HMI was shown in the direction of where actual also the hazard could be seen from the driver perspective. We mounted many different cameras in the vehicle. 2 cameras directed towards the driver for Cygnify to analyze the gaze direction of the driver during all the different tests, and several cameras directed to the outside world as a kind of context for the complete test. Go to the next one, and we see that we used this vehicle with the complete setup of the system in the field operational test in Eindhoven, where we asked 23 naive subjects to run the car over a route of 32 kilometers, and each round consists of 74 intersections, so 74 possibilities of potential hazard. We run 2 rounds for each subject, and 1 round was driving with the nudge system engaged, and 1 round was done without any nudging, to have a baseline to see what would be the difference of the nudging compared to the baseline situation. And as indicated, we measured the gaze direction and the response of the driver as, let's say, in speed selection for each of the intersections, to get an impression of how the driver responds to the nudges. In this case, as a field operational test, we really staged the simulation. You see that in the bottom right graph, where at let's say about 45 meters before the intersection, schematic representation of the intersection as a cross turns from gray to green, and the closer the car moves towards the intersection, the larger the cross in the HMI becomes, and the color changes from green gradually to red. We have done that in this way to make sure that all the subjects received the same type of input for each of the different intersections. Making a click to the next one, and these show the results regarding the gaze direction of the drivers, and we distinguish the 30 km/h speed limit zones and the 50 km/h speed limit zones. For the left graph, we indicated each bar indicates the percentage of time that the driver looks in the direction of the potential hazard, and this is averaged over all subjects, all participants in the test, and over all 74 intersections. The green bar indicates where the HMI was switched on, and the red bar indicates where the HMI was switched off, and it's clearly seen in both situations that with the HMI switched on, that on average the drivers look more in the direction of the potential hazard than without HMI. We also studied the effect on the individual participants, and that is the result there is shown in the table below. We see that for 10 out of 18 participants, they increase the intention in the direction of the potential hazard with the HMI switched on. There's no clear effect seen for 3 participants, and in 5 cases, we see a slight decrease in the tension in the direction of the potential hazard using the system. We not only look to gaze direction, but also to speed in the next slide, because speed selection, of course, also indicates how a driver responds to certain inputs. And here it's seen that although it's not significant for the 30 km/h zone, that still in the approach towards the intersection, the speeds indicated with the HMI switched on were slightly lower than the ones with the HMI switched off, and that was actually significant for the 50 km/h zone, where a 1 kilometer decrease in speed was seen in average on a about 39 km/h average. Also here we look to the individual participants, and we see that most participants decrease their speed in the approach of an intersection by when the nudging HMI is switched on. Brings us in a kind of overview of the results on the next slide. And I think the most prominent one is that at least in this reasonably short test, the test took about 2 hours for each participant to make those 2 rounds in Eindhoven, that for 56% of the drivers, they look more in the direction of the hazards as a result of the nudge. So we certainly can conclude that more than 20% of the test subjects increase their level of attention in the approach of a potential hazardous intersection, as was indicated as one of the objectives of the MeBeSafe project. Now, of course, there's many things to say to that. We come to the next slide. In this case, the HMI escalation was fully GPS staged, but even in this case, with a low level input to the driver, and we've actually asked the different drivers their opinion on how it influenced them, that they didn't feel any harsh interaction with them. So even if the HMI escalated in 54 times during the route, it stayed very effective, at least during that 1 hour period of time. There is uncertainty, of course, and that's because of the way we were able to set up the field operational test about the long-term effects. What is the habituation of drivers to such effect? So we have to see how the effectiveness might decrease over time when drivers get used to these inputs. But the system already is developed in such a way that we are able to inhibit the HMI escalation and increase the effectiveness in that way using the static hazard model and or the dynamic hazard model. So if we include the possible hazards in the field of view of the driver, then that is requiring a cyclist prediction model. And I really like to share the floor with Bram Bakker from Cygnify that will shed a light on that part of the project. Bram, the floor is yours.
Yes, thank you very much, Olaf. So this work is about the situation that the bicyclist is in view in particular, and we want to make the design or the nudging design more sophisticated by including prediction of what a perceived bicyclist is likely to do. So it's very much complementary to and an extension of the other work that Olaf described. And it's about these components displayed here in red in the overall architecture schematic that Olaf also showed earlier. Next slide, please. So this slide is about the roles of the various partners involved. Signify developed the core vision and prediction technology, deep learning base, which is our specialty. And in this picture, you actually see Bartos, my colleague, who did much of that work on the prediction technology. TNO did a lot of work on vehicle integration, on the radar, on the fusion algorithm for combining camera data and radar data. I'll talk a little bit more about that later. And also a lot of work about experiment setup and support. FCA finally supplied a very nice experimental vehicle, a Fiat 500X, and support for integration there and support for the radar work. So based on this combined effort, we did a structured controlled experiment just very recently, actually, end of July 2020, with simulated intersections and car-bicyclist interactions on the campus of TNO in Helmond. So it's very much complementary to the field operational test on real roads that Olaf described in the previous part. Next, please. Here's another view of the Fiat vehicle, indicating in particular the sensors and other special hardware that we used. So we're highlighting some cameras here, the radar, also important, which is shown the OXCS high accuracy location technology, which we use both for the vehicle and for the bicyclist to have really precise ground truth data about their trajectories, which is important for this type of evaluation. This picture also shows Alexis from TNO, who did a lot of work as well and was also the bicyclist. So as usual, we let the young kids do most of the work, and especially the dangerous job, in this case, riding the bicyclist. Of course, it wasn't really dangerous. We had a qualified test driver behind the wheel of the Fiat, and we made sure that all the situations were completely safe. Next, please. A slide about the advantages and disadvantages of this choice for a structured controlled experiment. Like I said before, This is very nicely complementary to the real-world field operational tests that we performed with naive drivers that Olaf talked about. And this is really focused on a controlled set of known hazardous car-bicyclist interactions. And an important advantage of this type of structured experiment is that we can obtain as much data as we like on such interactions. And those interactions are, during normal driving, very rare, fortunately. But in such a controlled experiment, we can simulate them for as much as we like without actually encountering real danger. Another important advantage, of course, is we can get really precise, solid knowledge on the ground truth bicyclist intentions and behaviors, and also the ego vehicle patterns. And a final practical advantage is that we can use experimental vehicle without road legal permissions and license plates. Disadvantages are there as well too, of course. A danger or risk is that, of course, in such a controlled experiment, the data might be less realistic than in real-world situations. We've tried to avoid it as much as possible, but it is, of course, a risk in this type of work. But overall, in balance, it's definitely a good choice, I think, to do this type of work in a structured control experiment. Next, please. This slide shows the various scenarios we tested. Those were derived from earlier knowledge on an earlier project, actually, in which TNO and Fiat were also involved on typical scenarios or scenarios, interactions between cars and vehicles, which relatively often lead to hazardous situations and accidents. So you can see different types of situations, like a bicyclist coming from one of the other sides of an intersection, but also situations like the bicyclist coming from the side or from behind the ego vehicle, or approaching from the front and making a turn in front of the car. So different types of scenarios which we all tested in this work. And I won't talk about all of them in detail, but this is just an overview of the different scenarios. And I want to highlight that these are really the most relevant scenarios in terms of accident risk. Next, please. A few words about the relevance and complexities of this prediction problem. Road user behavior prediction in general is one of the big outstanding problems for ADAS and self-driving car technology. And in fact, you see that now there is some more emerging work coming, including from very large companies like Waymo and Uber, about this type of road user prediction. It's really a big open problem in this space. And for bicyclists, even more so than usual, and there's a couple of reasons for that. And one of them, maybe the less important one, is that sensing bicyclists accurately is relatively difficult compared to cars, depending a little bit on the viewing angle, of course. And more importantly, bicyclists are difficult in the sense that they have very fast and flexible trajectories, and their trajectories are less constrained than those for cars. They don't necessarily follow the traffic regulations very precisely, you might also say. So there's really like a lot of variety in the types of bicyclist trajectories that one can observe. And we'll see later examples of that actually in other presentations later today. All this makes it really difficult to predict them. A little bit about the sensing. The main detection and tracking was done using camera technology and deep learning based algorithms from Cygnify. And those algorithms are really good at object identification and classification. We did initial position and speed estimates with that, and we improved the position and speed estimation by doing fusion with radar data. And TNO in particular did a great job at that, and has really improved the data a lot. In addition, we extracted information on body pose from the bicyclist, and in this picture in the bottom left you can actually see an example of that, and that can be useful in detecting legs moving, for example, for bicyclists. Head orientation, has this guy seen me, indicating direction with the arm, maybe. And in this work, this was more like a proof of concept. We couldn't really use it very effectively in the predictions, but we do think that this is very promising for future work. Next slide, please. So this slide illustrates the fusion some more. So again, camera data, when suitably processed, is very good for object identification and classification and stable tracking over time, but it's not great for accurate position and speed estimates. And radar, in contrast, is excellent for position and speed estimates. So in a sense, we try to get the best of both worlds. And TNO did a great job in building a fusion algorithm for this. And in general, in ADAS and self-driving cars, a combination of sensors like this, each of which with its own strength, is really a great idea. Next, please. Now, about the prediction algorithm itself, we developed a new algorithm called Hierarchical Probabilistic Social Scene, LSTM. I know it's a mouthful, but it really describes what it is about. It's deep learning-based prediction on multiple levels, 2 levels of a bicyclist's behavior. It builds on existing work in a nice way, and we pre-trained it on a very large open-sourced trajectory data set supplied by Argo.ai, which is an American self-driving car company, and we fine-tuned it on some limited data sets that we collected ourselves. Next, please. This slide shows basically the main input and output. The central idea is that the input contains multiple types of inputs. First of all, about the observed trajectory of a bicyclist. Secondly, about other road users around the bicyclist and about the ego vehicle, because these types of social interactions are important for prediction. And thirdly, a representation of the scene, a representation of the road layout. The output that we produce are actually predicted trajectories with the likelihood for multiple possible paths. And this is important. So we're not predicting just one most likely trajectory, we're predicting multiple likely trajectories. Next, please. Basically, the first step in this approach is that we have a high-level network which predicts for an intersection. Okay, this is the likely. These are the likely high-level destinations on an intersection, and there can be multiple of those. So, for example, bicyclists might go straight, or you might make a left turn, and we make predictions for each of them. So, this first high-level network predicts. Okay, these are the various high-level options, basically. Next, please. And in the second step, a low-level trajectory network takes for each of those high-level destinations the inputs and predicts, okay, what is the likely low-level trajectory for that high-level destination. So that is the one responsible for really making the precise trajectory path prediction. Next, please. Here is a demo video screenshot, and the link is provided here, and I recommend checking it out. It nicely illustrates what it is about. In the bottom right corner, you see the detected and tracked objects, in particular the bicyclists. And these objects are positioned in a 3D model shown on the left, together with a simplified HD map. And on there you can also see like the simulated intersection and the various tracked road users, and also the ego vehicle in blue and its intended trajectory with the blue dots there. Next, please. And this slide then shows an example of the prediction and the hazard detection. So on the left side, you see these 5 white dots, and they represent the predicted high-level destinations at that point in time. And then you see for each of those the predicted low-level trajectories as well, like these little paths consisting of small white dots. And the hazard estimation is done by a formula taking into account whether a predicted bicyclist trajectory path intersects with the ego vehicle path, the probability of that predicted bicyclist trajectory, and the time to collision if that situation would materialize. And the highest hazard in this case is highlighted by the red trajectory. Next, and here's another example of just prediction later in time. So the further in time we go, the more precise typically prediction goes. So now we're more certain that the bicyclist will actually make this left turn. Next, please. And here's a final one. It basically shows the same principle again. On the top right, we see a kind of concept of an augmented reality head-up display HMI solution, kind of similar to what was described earlier by Olaf, where you might highlight these hazardous trajectories from the bicyclist and also highlight the trajectory itself, hopefully in a kind of subtle nudging way. Next slide, please. It's my final slide. So first of all, we demonstrated the soundness of the multi-level prediction methods that I just briefly described here. We demonstrated the feasibility of the hazard detection and the warnings derived from this. We demonstrated the real-time functioning of this, and we demonstrated using post hoc processing really how such hazards could be used in an HMI. Next, please. In terms of expected value, we've collected lots of data and metrics, and are still in the process of some of the final analysis, to be honest. But one metric is really particularly interesting to highlight here. We find that the first valid hazard warnings are given typically between 3.5 and 5.5 seconds away from the potential collision points. So this means that the driver would still have about that time to react to it. And this is very nicely in line with the envisioned proactive nudging time zone that we have been aiming for in this project, and that Olaf talked about before as well. And so we're quite happy with this result. Thank you.
Yeah, thank you. First of all, Olaf and Bram for this really well elaborate insights into this work package on in-vehicle nudges.